we're going to take a step back now to talking about matrices. But before we can talk about them, I do want to introduce what is a matrix, right? So the idea of a matrix is it's a rectangular array of numbers, right? So an n by n matrix is a rectangular array of numbers with n rows and m columns. So this part, this n cross m, is what we consider to be, or what we call, let me write it here. These are our dimensions. And by that, it's telling us how many rows and how many columns makes up this matrix. And this is what it looks like. There's just a rows and columns, and each value is known as an entry. But there's this notation that you see here, these subscripts. So it seems like it's saying 11, 12, 13, 21, 22, but the idea is saying that this particular entry is your first row, first column. It's row 1, column 1, and that's your first entry. On this end, this says row 1, column 3. So we have row 1, and it's our third column. And that's how we think about these dimensions of a matrix. Now, it's important to understand what that means, because similar to vectors, if you didn't understand the notation of a vector, it would be difficult to apply the operations. Similar to these matrices, because we're going to be talking about algebra matrices. So now we're going to have to apply operations, as, and you can already see we have a addition, subtraction, and so on, and multiplication. But it's not your traditional. Some parts feel traditional in multiplying and adding and subtracting, and if you notice in vectors, we didn't discuss dividing the vectors, right? There was a multiplication of a half, right? But we didn't discuss this concept of dividing, because not all the algebraic operations and axioms can be applied in each topic. So this is just a quick intro to what a matrix is, right? A version of this in the real world, you can think about it as looking at a photo that's pixelated, right? If you zoom in on a picture that was, and that's now we have different types of photos, but when photos were first created, we had they were pixelated, and if you zoom in far enough, it's just a lot of little boxes of colors, and those particular colors, some are darker, some are lighter, are what creates the image. And that's this idea of what a matrix is that particular value for that color was represents a value, and then the next color next to it in the next row or the next column has a different value, and that's a way to visualize what a matrix is. But some of this first type of operations are pretty straightforward, right? Really nice in my opinion. Now, to be able to add or subtract a matrix, you really need to have this first one. So this is what you need, and this is how it's done. So what we need is to have the same dimensions. So if there's 2 rows in the first matrix, there has to be 2 rows in the second. There's 3 columns, and the second one needs 3 columns, need to have the same number of rows and columns. Because the way you add or subtract a matrix, you have to add or subtract the identical entry. So you add and subtract identical entries. What do I mean by that? This very first entry, we're going to take 2 and then 1. Because that is the same, that's row 1, back to how we represented row 1, column 1. That's what this 2 is for A, and that's what this 1 is for B. This is row 1, column 1. This is row 1, column 1. And that's what I mean by identical entries. We're just going to apply the operations. So here, I'm going to take 2 plus 1. And then I'm going to add -3 with 0. That's going to be -3 plus 0. And I'm trying to color code them so you can see that we are applying each entry. 0 plus -3, put that in parentheses. And then we have, let me change the color. It's going to be 5 plus 1. I'm running out of colors to choose from. Oh, I still got purple. Purple. That's going to be 7 plus 2. And lastly, I'm going to have to add one more color. Let's add some brown or yellow. We'll do yellow. Yellow and yellow. And that color, we'll add a yellow, which is going to be, it's going to be hard to see that color. Let me switch it to not orange. I'll use this magenta color. Hopefully you can see the one we added. I'll highlight it in yellow so that we know that's the corresponding one. But that's it. You just add corresponding coordinates. 2 plus 1 is 3. -3 plus 0 is -3. 0 plus -3 is -3. 5 plus 1 is 6. 7 plus 2 is 9. And then a half plus 2 is -half plus 2 is -3 halves, right? Or if you take a half away from 2, you're left with 1 1/2. And that's what 3 halves is. And it would work the same way with subtraction. You would just subtract the corresponding or identical entries. Now another algebraic operation is multiplication. But if you notice, we do have multiplication of matrices, and then we do have this idea of scalar multiplication, which is going to be similar to what we saw with vectors, right? That we would the scalar multiplication would either make the vector longer, shorter, change direction. But the way we applied that type of multiplication, it was just to each component of that vector. Well, this is going to be very similar. All we're going to do is apply that scalar to each entry in the matrix. So it almost seems like distribution. 4, -6, 2 times 0 is 0, 5 times 2 is 10, 7 times 2 is 14, and -1/2 times 2 is -1. And just like in vectors, we can apply both of these ideas, right? We can find 2c minus 3d. Now, I can start by dealing with the scalar first, meaning I'm going to multiply to each entry by 2. So So that's going to give me 14, negative 6, 0, right? And this is coming straight down here. This one's coming straight down here. So we have 0, and then 2 times 0 is 0 again. 1 times 2 is 2. 2 times 5 is 10. And then I'll handle 3D. So I'm not applying the negative in. I'm just going to subtract them from each other. So that's going to give me 3 times 6 is 18. 3 times 0 is 0. 3 times negative 6 is negative 18. 3 times 8 is 24. 1 times 3 is 3. And 3 times 9 is 27. Now all I'm going to do is subtract corresponding coordinates. So instead of writing it all out like the previous one, 14 minus 18 is negative 4. 0 minus negative 6 minus 0 is negative 6. 0 minus 18. Now you have to be careful because it's minus a negative 18, which those two negatives become positive. 0 minus 24 gives us negative 24. 2 minus 3 is negative 1. And 10 minus 27 is negative 17. Now, you can start seeing why we need the dimensions to be identical. Because if the dimensions were not identical, there would be an entry that does not match with the matrix that you're trying to apply that algebraic operation. So, for example, here, this is so remember we have to list the number of rows. So that's a 2 by, and then there's 3 columns, a 2 by 3 matrix. This next one is a 3 by 2. But these are not equal to each other. And because they're not equal to each other, we cannot add them. Even though, yes, we'd be able to add the first entries together, the second entries together, but when we get to that third entry in the first row, there is no additional number to add with. So that's why we need the dimensions to be the same. So in other words, this is not possible. And this is pretty quick, right? That's why I'm going through it a little fast. It's self-explanatory in some of these ideas. Now, the one that is a little trickier to grasp is this multiplication of matrices, right? Which in vectors, we also had the scalar multiplication and then the dot product. But the way you dealt with it worked a little differently. Same with multiplication of matrices. There's a pretty set procedure. Not a pretty, there's a set procedure on how you do this operation. And that's the part of learning how operations behave within this context, or with vectors. That was a different context, and we needed to understand that. So the multiplication of matrices. The product of two matrices A and B is defined only when the number of columns equal, I should put is, but I hope you understand, equals the number of rows in B. So it's a little tricky. For adding, subtracting, scalar multiplication, there's not really much to think about. The scalar multiplication, you distribute that scalar into each entry. Adding them, you just add corresponding identical entries. But for multiplication, there's something that needs to be true for matrix A, and there needs to be something in matrix B. So now there's more verification than just seeing if they're the same dimensions. So it starts with the first column you're multiplying with. You need to have the number of columns in this matrix needs to be equal to the number of rows in that second matrix you're multiplying. Now, this is why I said there's some axioms that don't apply with matrices. For example, multiplying the commutative property of multiplication with matrices does not always exist. Sometimes it works, sometimes it doesn't, because you might not have these matching dimensions. So those, if you list them out next to each other, you need to have these two equal. Now, something to take away from this, from these dimensions, is when you do multiply, a way to verify that you are, because it's very tedious in the way you multiply, you want to make sure that your resulting matrix comes from the number of rows in A and the number of columns in B. And that's what your resulting matrix is. So you can think about the inside needs to be equal, the outside is what you're going to be left with. Now that's just what you need to apply the multiplication and what's going to be the resulting matrix when you're done with the multiplication. But there's an entire process, and it's a very detailed, technical, tedious process of multiplication. Now, this is just I didn't want to make it very wordy, so I created this very small description, very hollow description, I would say. Just because if I started explaining each single detail, it would be one very long explanation. But to keep things simple, you multiply each row from the first matrix, so in this case the one that's on the left, with each column of the second matrix, that's the one on the right. So to make it even shorter, we multiply each row with each column. Row and column, row and column. So that's a way to remember it, is you're taking the row and multiplying it with the column. Now, how does that look? Well, let me show you in this quick example here. Luckily, this is a 1 by 3 matrix because there's only one row, but 3 columns. Now, for D, it's a 3 by 1 matrix because it has 3 rows but only 1 column. Luckily, the columns in C are equal to the rows in D. So because they are equal to each other, these two values are equal, then we can apply our multiplication. Now that means I'm going to take this row and multiply with this column. Now the tricky part is, how do I multiply them? Well, the idea is you're going to take this row and you're going to turn it, right, upward. You're not going to turn it downward. That would change your answer. You're going to turn this 90 degrees to the right and make it vertical. Because the moment you can make it vertical, you would take and multiply across. So, let's do it. So I'm going to change that row for C and write it into 1, 2, and 3. Because I rotated it in the clockwise direction. And that would make this vertical. I already have D vertical, and that's why I need those to match, because if this was a slightly different dimension, I wouldn't have the entry to multiply with. Now, what are we going to do with all these? You're going to multiply them all together. So you should have multiplied straight across. 1 times 3 is 3. 2 times 4 is 8. And 3 times 5 is 15. Now, you have to take each one of these products and add them together. I probably should have wrote this differently, because it seems that it became one single column, but it's not really becoming a single column. This multiplication, this is row 1, column 1. So in other words, if you see the dimensions, I multiplied row 1 with column 1. So this is one entry. So I take 3 plus 8 plus 15, and that gives me 26. And that would be my answer of this multiplication. But because of how small it is, it does make it tricky to understand. But remember what I said, that the outer dimensions is your resulting matrix. There is one row here and one column. Hence, row and column. That's why there's only one entry. Now, we move on to another example. I forgot to write down what F is, but I can write it down as we're talking. So, you want to make sure you start by looking at what your dimensions are. So here I have a 2 by 2 matrix. This is a 2 by 3. Now these two are equal. And not the dimensions, because clearly 2 by 2 is not a 2 by 3, but the column and the row are equal. Hence, that's going to leave me with a 2 by 3 matrix. But this is a part where it does get lengthy, because we're going to be doing this multiplication process about 6 times. So like I said, we take the first row and multiply it with the first column. You rotate that first row 90 degrees clockwise, and that's what gives you a vertical row. And then you're going to multiply straight across. And that's going to be 1 times -1. And you're going to do that for each one. So right now I just did 1 times -1, but I still need to add it with 3 times 0. Because if I rewrite this row into a column, it would be 1 and 3, and you're just multiplying straight across. But you have to add those products together. And this is to make up row 1, column 1 entry. Now I'm going to take the first row and multiply it with the second column. It's almost going to resemble distribution. So if I think about rotating this clockwise 90 degrees, it would be 1 and 3. But I have to multiply 1 times 5. This is going to be 1 times 5 plus 3 times 4. And then I do it one more time, and that's going to be 1 times 2 plus 3 times 7. And that was taking this first row and multiplying it to each column. Now I take the second row, rotate it again, clockwise 90 degrees, and multiply across, and you add the products together. So -1 times -1, this is first entry, or second row, column 1, so A sub 1, A sub 2, 1. Plus 0 times 7. Sorry. I was looking at the last one, but for second row, first column, -1 times -1, 0 times 0. Now, second row, second column. We'll go a little quicker now. So this is going to be negative 1 times 5 plus 0 times 4. And the last one is going to be negative 1 times 2 plus 0 times 7. So I have to multiply and add. Of course, 3 times 0 is 0, so this gets canceled. And then negative 1, or 1 times negative 1, is going to give us negative 1. 1 times 5 is 5. 3 times 4 is 12. 12 plus 5 is 17. And then 1 times 2 is 2, plus 3 times 7 is 21. 21 plus 2 is 23. And now, here, negative 1 times 1 is still negative 1. Negative 1 times 5 is negative 5, but 0 times 4 is 0. So that's going to give me negative 5. And then negative 1 times 2 is negative 2, but 0 times 7 is 7. And then you have a negative 2. Oh, this one should be positive, because it's the first row with the, or wait, I might have made a, yeah, first row with first column. That should have been a negative 1, and I missed it here. That's why this one's really tedious. There's a lot of little moving steps, and you can make easy errors. Now, something to point out, or let's do one more example. Again, I forgot to write what the matrix B was. So it's 3, negative 1. And you can pause any of these videos at any time and try to do the example. So I'm going to take first row, first column. So if I change the 2 and 1 vertically, it's going to be 2 times 3 plus 1 times negative 5. When I distribute to the next one, it's 2 times negative 1 plus 1 times 2. And then we're going to take the second row now and multiply with each column. So 5 times 3 is, or I'll just put 5 times 3 plus 3 times negative 5. And now the second row with the second column, it's going to be negative 1 times 5 plus so negative 1 times 5, and then plus 3 times 2. And of course, they are equal to each other, right? Something I forgot to illustrate even on this previous one. If you notice, this resulting matrix has to be a 2 by 3, which is exactly what this matrix is. It's a 2 by 3. So here, we didn't check it, but this is a 2 by 2 and a 2 by 2. Hence, they're equal. That means I can multiply A and B, and my resulting matrix should be a 2 by 2 as well. Now, we have everything multiplied. Now we just need to input it. So 2 times 3 is 6 plus negative 5 is 1. 2 times negative 1 is negative 1 plus 2 is 0. 5 times 3 is 15 plus, or sorry, yeah. I made an error here. Second row, first column was 5 times 3, but this 3 shouldn't multiply with this negative 5, and I wrote negative 3 here. It should be negative 5. Because 3 times 5 is 15, plus 3 times negative 5 is negative 15. When you add them, it gives you 0. Negative 1 times 5 is negative 5. And then 3 times 2 is 6. And that's going to leave me with 1. And lastly, really quick, looking at these two matrices, say 1, 2, 3, and then 4, 4, 4. What you want to be careful, even though they're both have the same, right? This is a 3 by 1. This is a 3 by 1. They both have the same dimensions, but that's not what I'm looking for in multiplication. I'm looking for the number of columns from row 1 to be equal to the number of rows in row 2. And they are not equal to each other. So these numbers are not equal. So that means this multiplication is not possible. The nice thing about these, you can literally make up your own examples. Again, it's not possible because it doesn't have, they don't share equal dimensions for columns and rows. But if you want, try your own examples. Just switch up the matrices, use different values, and see if it's possible or not, and then practice that rotating of 90 degrees, multiplying straight across, and then adding those products together. We will look at how this is applied in the next section, but I'll stop this here.